To begin to understand nutrient cycling to terrestrial ecosystems, we'll start by understanding nitrogen inputs. And of those, we'll begin with fixation. Biological nitrogen fixation is the main pathway by which new nitrogen enters unpolluted terrestrial ecosystems. So when we think about nitrogen inputs, we're going to start with fixation, and this is the main pathway by which nitrogen is going to enter unpolluted terrestrial ecosystems. So ecosystems that aren't receiving a lot of anthropogenic nitrogen. The pathway of nitrogen is facilitated by plants. So when you go to an ecosystem and you see acacias, for example, these are plants that are associated with nitrogen-fixing bacteria and serve to provide the energy for a lot of nitrogen to enter into the system. In other ecosystems, it might be legumes, like this Baptisia, that are associated with the microbes that fix a lot of the nitrogen that enters into ecosystems. Whereas in aquatic ecosystems, we're going to focus in on cyanobacteria. Now, the process of biological fixation takes nitrogen gas and reduces that to ammonium. So nitrogen gas, nitrogen is going to be at a state of zero charge, and this end here is going to be at -3. So that in and of itself takes a lot of energy. But there's another thing that has to happen first, and that's a triple bond that has to be broken. So N2 is linked by a triple bond. And the activation energy, the amount of energy that it takes to break that bond so that hydrogens can get added, is pretty substantial. So the first thing that has to happen is that triple bond has to be broken. That's not easy. In order to facilitate this, microbes use an enzyme called nitrogenase. What nitrogenase does is reduces the activation energy, or the amount of energy required, to break that triple bond. That in and of itself is a good thing, but nitrogenase itself is denatured by oxygen, which means in order for it to be effective, it has to exist in a low oxygen environment. In addition, there's high energetic requirements still to provide the activation energy to break the triple bond of nitrogen gas. And so temperatures have to be relatively high and carbon availability has to be high to generate enough energy in order to break that bond. Most of the nitrogen fixation that occurs happens through a symbiotic process. Here's table 9.1. And this table shows the organisms and the associations involved in dinitrogen fixation, so the fixation of nitrogen gas to ammonium. This is the type of association in this column and some of the key characteristics of that association and the representative genera of microbes that actually end up doing the fixation itself. So for heterotrophic nitrogen fixators, that the bacteria are primarily doing the fixation. That means because they're bacteria, their energy source must come external to their organism. Those are often provided by plants. So associative nitrogen fixation can occur in a nodulated system. Legumes, for example, are associated with rhizobium, while non-leguminous woody plants, such as alders, tend to be associated with a different set of bacteria, the Frankia. Now this happens in nodules that are produced by the legumes or the woody plants, but there's also non-nodulated systems too. Lastly, we have, in addition to associative, we have free-living So the associative heterotrophic nitrogen fixers are associated with plants, but there's also free-living nitrogen fixers that occur in aerobic and anaerobic environments, for example. Now, in addition to heterotrophic nitrogen fixers, there's phototrophic nitrogen fixers that rely on the sun for their energy, such as cyanobacteria. And these phototrophic nitrogen fixers can be associated with symbioses, such as in lichens, mosses, or ferns. And I think in the book they talk about the water fern, Azolla, for example, and its association with nostoc. In addition, you can have phototrophic nitrogen fixers that are free living. Again, these are still cyanobacteria, and nostoc is an example of a cyanobacterium that can be associative, such as with the water fern, or free living. Now, the rates of nitrogen fixation are a lot higher when it's associated with a fern than not, but both can occur. So to recap, we have heterotrophic nitrogen fixers and phototrophic nitrogen fixers, and the heterotrophs, representing the bacteria, can be associative or free living. In the same sense, the phototrophic nitrogen fixers, which tend to be cyanobacteria, can be associative, so they're symbiotic, or free living. The symbiosis is important for two reasons, if there is a symbiosis, and that's because plants can provide a lot of carbon to the bacteria and an anoxic environment. For the plant, though, providing carbon to nitrogen-fixing bacteria is a lot more expensive than acquiring inorganic N if it's available. So if inorganic N is available, it's somewhere on the order of 1/4 the energetic cost to acquire inorganic N than it is to actually fix N and turn it into ammonium. So in that sense, if inorganic N is around, there's not much benefit to using microbes to fix that N.